Thank you, Enrico. Thank you very much. It is really a pleasure to be here. This is a wonderful place that I visit for the first time. So, the aim of these lectures is to discuss the foundations and the limitations of this modern approach on the nuclear interaction, an approach that was initiated by Weinberg in the in the 90s. In the 90s, and I entered this subject around 15 years ago, so halfway. And already at the time there were very sharp controversies about issues like renormalization, like power counting, renormalization in the non-perturbative way, not the perturbative renormalization that one is used to. And I must say that after 15 years, these controversies are not settled yet, and they are still on my desk. They are they are growing in height. So this means that they are rather non-trivial issues, very subtle points that I decided not to discuss in detail. Instead, I'll try to focus on the fundamentals. I'll try to recapitulate the logical steps that lead to the development of let's say, modern chiral interactions. And this is goes under the name of chiral effective field theory. So let me first discuss my understanding of this term, effective field theory. And I have a strategy when I have a dissertation with a title. A reasonable strategy is to ask oneself about the meaning of the different words. Effective field theory. This is my uncle used to tell us about a classmate of his that had this strategy. When he had to do the dissertation, he had an algorithm. He would look in the dictionary each words of the title of the dissertation, and then would transfer the entire item of the dictionary in the dissertation. At the end, he would end up with a decent two-page dissertation, which was not brilliant, but at least he could score 4 out of 10, which was, in his opinion, better than nothing. So let me try to do the same and discuss the meaning of this word effective. Effective means something which works. But this is not the only meaning. Something which also, I like to contrast this word effective theory with the word model. Also, a good model is a model which works very well. But here effective is the adjective of another word, which is theory. And theory is a Greek word that I am not an expert about. I'm very ignorant about etymology. But I think that one of the accepted differences between theory and model, there are mainly two differences. One is concerning the scope. The scope of a theory is much broader than models. And another aspect, very important one, which is related to the first one, of course, is the predictivity, the predictive power of theory, much more than for models. Even though models can be very encompassing, it is quite funny that the most encompassing theory of natural of the working of nature at the most fundamental level is provided by a theory which is known as the standard model. But indeed, even the standard model, the modern understanding of the standard model is itself as an effective theory of some more general framework which we don't know about, and perhaps we will never be able to know about. It doesn't matter. Still, effective theories provide the tools to make predictions with controlled uncertainty, even in the absence of a knowledge of the fundamental theory. And between effective and theory, there is this word field. Field because the ingredient of this description is in terms of fields. And this is inevitable if the description is to respect the requirement of relativity. Relativity is a very important constraint, symmetry constraint. Yes, it is very unfortunate that in this terminology, the term symmetry is missing, because symmetry is really a crucial ingredient for the effective field theory framework. So instead, it was missing. Let us take this word chiral as an example of these aspects of an effective field theory. The importance of some symmetry principle. And relativity is a symmetry principle that we are very confident about. Of course, in a relativistic description, the appearance of fields instead of particles is inescapable. But for a large part of nuclear physics at very low energies, this is not inevitable anymore, the term field. At sufficiently low energy, we can forget about creation of particles and arrive at quantum mechanical, ordinary quantum mechanical description. For this reason, sometimes this letter F does not appear, and one reads about chiral effective theory, because the language of field theory, at least for a small number of particles, is not necessary. Of course, when the particles become starts to become more numerous, then the concept of field is useful again. But I like to maintain this letter F here, and to start with, give you some well-known examples of effective field theories, well-known effective field theories. To make a distinction between so-called decoupling effective field theories and non-decoupling effective field theories. So for example, one of the first instances of effective field theories is due to the work of Euler. Euler, not the mathematician. He was his relative. Euler, Heisenberg, Lagrangian, to describe the interactions of photons among themselves for energies much smaller than the mass of the lightest charged particle, the electron. So as you know, the photons do not interact among themselves, but for energy sufficiently low, then they can scatter among themselves in a diagram of contact type like that, which is the low energy lepton of more fundamental diagrams, which proceeds through the exchange of charged leptons, of charged whatever, a charged particle, that is this box diagram. if these particles, intermediate particles, let's say, are very highly virtual, then if the energy is much smaller than the mass of these particles, then they are highly virtual, off shell, and we could say that they don't live enough time not to propagate, and the interactions shrinks to a point. And this is captured by an effective Lagrangian. So the QED, which in this case is the theory, the fundamental theory, is which is okay. This is the term which is present also in QED. Then there is the term which is present, which describe the charged particles, the matter fields. This we can forget about, okay? And the effect of the leptons show up as additional interactions of the photons, of the ingredients of the theory at very low energies. And so in addition to the terms already present in the fundamental theory, there show up further interactions of the photons among themselves, which are of this type, F mu nu square, with some coefficients which we could call A, plus B F mu nu F nu F, well, I should pay attention with the F nu rho, F rho sigma, F sigma mu, like that, okay? There are these two extra interactions and a lot more, okay? Actually, there is an infinite number of interactions, because by allowing intermediate exchange of charged particles, also we can have vertices with participating 4 photons or even more, 6 photons and so on. There is a whole theory of a whole hierarchy of new terms which appear in the effective description, which are only constrained by symmetry. Why I could write terms like that? Because this is the only terms which are invariant under the underlying symmetry. In this case, is the gauge symmetry. So the photons can show up only in the form of this curvature F mu nu. So, and there is no term like that. Also, Lorentz symmetry is no rho F rho mu. A term like that is with 3 curvatures is identically 0. You can prove as an exercise, so it is absent. The term with the lowest dimensionality that we can write is this one. Actually, there are 2 of them, which respect the Lorentz invariant and the gauge symmetry. Okay. So, and we can do a matching between the fundamental theory and the effective theory, and obtain, as Euler-Heisenberg did in the 30s, numbers, exact numbers for these coupling constants, new coupling constants, A and B, in terms of the ingredients of the fundamental theory, for example, the mass of the charged particles and so on. But in order to do the calculations in the low energy regime, we only need these 2 terms. So it is a more economical description. It's much easier also. This is another meaning of the word effective. Effective means which works in a much simpler way. Okay. So it is enough to know these numbers, in principle, could be derived by the knowledge of the fundamental theory to perform calculation. Okay. And another well-known example, which conceptually is exactly the same, concerns the weak interactions, which is at the origin, for example, of the beta decay, okay, in which we have an exchange of gauge boson W for energies much smaller, for momentum transfers much smaller than the mass of this W particle. This W particle is highly virtual, and so the interactions shrinks to contact interactions. for fermion interactions, like Fermi developed for his theory of beta decay. So a common feature of these two examples is the fact that the ingredients of the fundamental of the effective field theory are a subset of the ingredients of the fundamental theory. The heaviest modes of the fundamental theory simply decouple. Okay, their effect become subsumed in the value of these coefficients, which are called low energy constants. But this is not always the case, and this people often refers to these situations as examples of decoupling effective field theories. It is not the only possibility. Sometimes the very ingredients of the effective descriptions are very different from the underlying fundamental theory. And something new emerged, something which was not written in the original fundamental theory, One well-known example, important also historically, is the theory of the superconductivity, is the Ginzburg-Landau theory of superconductivity. In the Ginzburg-Landau theory of superconductivity, we don't know, we don't talk anymore about electrons, ions, whatever. No, the description is in terms of some other ingredient, so-called order parameter. Okay, the order parameter, I don't know, psi. Okay, which is related to the density of the superconductor of the Cooper pairs, we could say, okay, in the microscopic description of the superconductivity. Macroscopically, all is written in terms of these new degrees of freedom, psi, which enter in the expression of the free energy, for example, and one sees that the ground state of the systems, okay, does not respect the same symmetry as the theory itself. Okay, in this case, the gauge symmetry. So we have the phenomenon in supersymmetry of so-called spontaneous symmetry breaking. So in the condensed matter setting, this is rather well known, and it was really this superconductivity the starting point for Nambu of a concept which he translated into the particle and nuclear theory, the concept of spontaneous symmetry breaking. Okay, and it means something, a phase transition, something very different between the fundamental theory and the effective macroscopic description. Macroscopic in this case means low energy. Okay, for us. Okay, there is this parallel between field theory and thermodynamics. So and and this through the via Nambu, this brings us back to the to this term chiral. Okay, chiral, which which is a symmetry of the underlying theory. Underlying theory in this case is QCD, which is very easily written, the fundamental Lagrangian plus f psi e the slash minus mf psi. This is the Lagrangian of QCD. It is a theory of quarks and gluons. Gluons play the same role as the photons in the previous example, but more complicated. They interact among themselves in particular, and it makes all difference. And then a series of matter fields, the quarks, which interact with the gluons via these covariant derivatives. Actually, there are 6 flavors. This F is a flavor index, 6 species of quarks. But we can, for most of our purposes, forget about the heaviest quarks and concentrate on the light quarks. up and down quarks. And even we can also simplify further the theory by considering the so-called chiral limit. It means these light flavors are really very light, and it is a very reasonable approximation to neglect their masses. And so the Lagrangian simplifies further and displays asymmetry, as I will explain now, because we can, in this case, okay, collect the quark, the matter fields, the quark, in a doublet up and down, which we can rotate by unitary transformation, which we can rotate, and the Lagrangian will still remain the same. Instead, moreover, if the mass term is absent, we can independently rotate the left and the right chirality of the quark. Left is left chirality, this is the right chirality, this projection, and this is the left chirality. As you know, the mass term mix the chirality, because when we write the mass term like that, psi bar psi, this is involved the different chiralities of the quark fields. So if this mass term is absent, each chirality lives his life independently, and we can rotate independently these two flavors for the left and right chiralities, because the because the kinetic terms, these ones, are diagonal in chiralities. The kinetic terms we can write like that in terms of terms involving only the left chirality and the right chirality. So this rotation can be done independently in the two chiralities. We can rotate with a unitary transformation the left doublet and the right doublet, psi r, yeah, psi right, and leave in this way the QCD Lagrangian invariant. Okay, so these are unitary matrices belonging to SU2. Okay, SU2 left and SU2 right. And for this reason, the symmetry is SU2 left cross SU2 right. Okay, this is the chiral symmetry of QCD. The possibility to independently rotate left and right chiralities of the quark, of the light quarks. Yes, please. I'm sorry. Yes. Okay, this did you follow the discussion about the QED, the discussion about the photons? Okay, so and so. I'm sorry. Okay, actually, the QCD is only the starting point. We will soon employ a different language. So this is a term in the QCD which contains the dynamics of the gluons. The gluons. It is a theory of quarks and gluons. QCD is a theory of quark and gluons. And the theory of the hadrons, of which is pertinent to nuclear physics, is not a theory of quark and gluons. It is a theory of hadrons. Okay, and we will, in the same way as the theory of superconductivity, a fundamental theory of superconductivity is about electrons, Cooper pairs. And the macroscopic theory of superconductivity is a theory about this order parameter psi, which is related to the Cooper pairs in a very indirect way. So the two descriptions, quark and gluons, and from one side, and hadrons from the other side, are completely different. It is an example of what I was calling non-decoupling effective theory. So actually, this is the fundamental theory that we don't know. We don't need, I'm sorry, we know it, that this is the theory, but we don't need to know the exact working of this theory. Actually, it is a mystery. After 50 years, this theory, it is simple to write the Lagrangian, but it is very difficult to derive predictions. So to continue, this is the terms which describe the gluons, and this is the terms which describe the interactions of the quarks with the gluons. This symbol here, the covariant derivatives, contains this T mu psi. Exactly, this means G mu psi. Okay, these covariant derivatives is involves the gluon field G, okay, which realizes a coupling of quarks with gluons. In diagrammatic terms, it means something like that. The fact that the quarks interact with the gluons in this way. Okay. I can skip the fact that okay. Well, I don't want to, really to discuss the QCD. I just need the analogy with the actually with the quantum electrodynamics that we were discussing before. So, so they don't play any role in this transformation, in this chiral symmetry. The gluons do not play any role. Instead, the quarks are the main actors, so to say. So, which undergo this transformation. Okay, if we transform these fields, the quark fields, by mixing among themselves these two flavors up and down, then the Lagrangian is left invariant. You know, the mixing of up and down quarks is the same as the isospin symmetry, of the strong interaction. It is related to the property of charge independence of nuclear force. Okay, but actually the symmetry is something more. It is more than simply isospin symmetry. It is the double, so to say, of isospin symmetry. It is an isospin symmetry for the left chirality and for the right chiralities. Okay, where chiralities are defined in this way. Okay, so it is a twofold, let's say, isospin symmetry, the one which we are discussing here. So, okay, this mixing, this rotation of the two flavors up and down of quarks for the left and right chiralities is realized through this SU2 matrix, okay, which we can write in terms of the tau matrices, substantially through. So this is the general expression of the most general SU2 matrix, which we can use to mix among themselves the up and the down quark. Okay, and these are the Pauli matrices, so the generators of the SU2. And these are the parameters alpha of the transformation. It is this group is three-dimensional, so there are three independent ways of doing an SU2 rotation, an SU2 mixing of these quark flavors, and so these transformations depend on three arbitrary parameters that we call alpha A. A is an index here. A is an index which runs through three values, 1, 2, 3, as the three Pauli matrices. So we have the possibility to choose at will three numbers, okay, rotate the left chiralities of the quark fields and leave the Lagrangian invariant, okay? And also we can do the same with the right chiralities in a completely independent way with another set of parameters, alpha A, R, okay, different parameters, which we can choose at will to produce a general SU2 matrix by which we mix the quark flavors, the right-handed quark flavors. Okay, so we can choose six numbers arbitrarily and transform the fields of the Lagrangian in this way by multiplying the doublets, left-handed and right-handed, with this SU2 matrices independently, and the Lagrangian is left invariant. So it's a continuous symmetry, 6 parameters continuous symmetry, and which leaves the Lagrangian invariant. And therefore, by the Noether theorem, there are conserved currents that you can easily derive. They are associated with these symmetries. So there will be Noether currents J mu for each one of these independent transformation, and J mu right. Okay, this is the explicit expression of these Noether currents. You can derive very easily, and you can do it as an exercise. I will explain how to proceed. Tau A to psi. You could prove that corresponding to these transformations, there are conserved currents, Noether currents like that. Gamma mu tau A psi right. Okay, Noether currents. It means that okay. So one way to derive these Noether currents is to pretend that the parameters alpha A, R for example, depend on the space-time. Then the Lagrangian is not left invariant anymore if the parameters depend on the space-time. If this symmetry is not global symmetry, as we say, but it is a local symmetry, then the Lagrangian is not left invariant anymore, because we have an extra term which involves the derivative of this transformation matrix. Okay, so these derivatives is gamma mu d mu. If we subject the quarks to this transformation, space-time dependent transformation, then the Lagrangian acquires an extra term, which is the following: psi bar left, v left cross, I gamma mu d mu v a L psi L. Okay, so the Lagrangian, this is what is left over. And from this variation of the Lagrangian, you can read the Noether currents. Actually, this delta L can be written as the product, a Lorentz invariant product of a 4 vector, which is the Noether current, times the derivative of this parameter alpha. Okay, I was talking about here alpha AL x. So there are 3 parameters and correspondingly 3 Noether currents, one for each parameter of the transformation. Okay, so from this expression, by writing V in terms of the parameters, as is written above, you can derive the variation of the Lagrangian for space-time independent, a variation which vanishes if the alpha are global. They don't depend on the space-time. If they are global, then this variation is 0 and the Lagrangian is invariant, and we have the symmetry. If instead the symmetry is local, then the Lagrangian is not invariant anymore, and there is a variation of the invariance, which involves this 4 vector, which is the vector, the nether current, And the nether current imply the existence of associated charge, con constant charge, okay, from the these charges are conserved, these currents are conserved in this sense. Okay, that therefore divergence of these currents is 0 in the symmetry limit. And also it is the same for the right and the left nether currents. And this implies that the corresponding charge, there will be one for the left and one for the right symmetry. And these charges are the space integrals of the temporal component of the nether currents are constant. They do not depend on the space, on the time. I'm sorry. They do not depend on the time. Okay. Yes. Yes. The current is no, well. It is like that. The current is conserved on the mass shell. Okay. So the Lagrangian is invariant if these parameters are space independent, okay? If the transformations are global, then the Lagrangian is invariant. If we transform in a local way, okay, the Lagrangian is not invariant anymore, okay? So we have an extra term in the Lagrangian. The Lagrangian is useful to compute the action, okay? Action is the integral of the Lagrangian density, like that. Okay, so the action will change if we do these local transformations by some amount. Okay, this goes to s plus some delta s. Okay, some delta s, which is this delta s is exactly the integral of this delta L. Okay. But remember that the action, if the fields respect the equation of motion, is an extremum, I would say, is does not change. Okay, the action is stable with respect to any variation if the fields satisfy the equation of motion. Okay, so you can do once you integrate this variation of the Lagrangian over all the space-time, you can do a partial integration and change, okay, this alpha A, these derivatives will act on the nether current, okay, and you will end up with the integral of the, okay, this delta S. Let me do this in detail. So delta S is simply d for x of delta L is equal d for x of nether current d mu alpha A L of x. Okay, so by doing a partial integration, you will have d mu g x alpha A L x. So you will have a variation of the action. But now if the fields satisfy equation of motion, no matter what transformation you do, local, global, then the action is stable, okay? The delta S is 0 for any value of these parameters. So this is the reason why the nether current is conserved. So the reason to say that this d mu j mu is equal to 0. Okay, so is it the logic clear? So in the exercise you have to prove that the nether currents are as I have written, and then you have to prove another thing. Okay, another thing, which is the fact that the corresponding charges actually these corresponding charges, there will be 3 charges, because there will be 6 charges indeed, one for each for each independent parameter. So these 3 charges will satisfy the group algebra, in this case the SU2 algebra. Okay, this also you can prove. Okay, the fact that the corresponding charge uh, actually they generate the minus tau alpha psi l. They generate the transformation in this way. Okay, it means that under the transformation, this is psi l minus I alpha e L tau psi L. For infinitesimal transformation, it is like that. They generate transformation. These constant charges are also the generators of the transformation, of the symmetry transformation. In order to prove all these things, you can use the canonical commutation relation, the canonical anti-commutation relation, the fact that the equal time, okay, commutation relation between the fields and the canonical conjugate of the fields at equal time. This is canonical commutation relation. Okay, for fermions, it is like that. Okay, this canonical momentum in the case of fermions is simply I psi dagger. This is the expression of the, starting from the Lagrangian, you can derive canonical momenta of the fields and impose the canonical commutation relation, which you can use to prove the fact that the conserved charge, that the constant charge are the generators of the symmetry transformation. Okay. So classically, so the content of the symmetry is the fact that the nether currents are conserved. Conservation of charge conservation, for example. Okay, the currents are conserved. In the quantum theory, this translates in relations among the Green functions of the theory, among correlation functions of the theory. Okay, for instance, if you consider time ordered correlation functions of operators involving this nether current, this correlation function, you can view this q mu as related to the derivative of the current, and use current conservation to establish relations among different Green functions, among Green functions containing different operators. Okay. Why these nether currents may seem rather abstract objects. Indeed, they are very concrete objects. the nether currents of the chiral symmetry, because the nether current of the chiral symmetries are physical currents. They are the weak currents. To these nether currents that I have written there, couple the gauge bosons. For instance, the W boson of the standard model coupled to this exact current. So there are particles which are weakly coupled to the nether currents. Therefore, green functions involving these nether currents are very relevant for the properties of physical particles, okay, because they enter matrix elements of beta decays, for example, or of electromagnetic currents. So the fact electromagnetic current is just one example of this nether current. It is the nether current of another symmetry, which is the U1 symmetry. I don't have a clock here. So there may be a clock. No. I should hurry up. Break when? In 5 minutes? Yes. So let me sketch another concept that I would like to convey is technique to resume all these relations among green functions. All these are called word identities. Word identities. They are consequence of this current conservation. Consequence of current conservation. Word identities, they are identities which relate different green functions, time-ordered correlation functions of operators involving the nether currents. And all possible word identities deriving from the chiral symmetry are can be written down very in a compact way using the so-called technique of external sources. So this will take some time. So if we have to stop for 5 minutes, how much? Okay, 10 minutes. We stop now and we continue in 10 minutes. Okay, let's try to start again. So I ask you to please tell me about some of you know these things very well. Some of you see these things for the first time. I want to speak to everybody, so please tell me if you don't know. It's not that you don't understand, simply don't know the meaning of something which is written in the blackboard, because not knowing the things is the starting point for the knowledge. I think we should give importance to the ignorance, to the fact that we don't know the things. This is a very beautiful situation when you don't know something, because it means that you can enlarge your knowledge, and this is our everyday job, to be honest and say that I don't know this thing, so perhaps I don't understand this thing, and let me try to understand it better. This is the starting point for expanding the knowledge. Your knowledge may be the knowledge of someone else. So if you ask a question to enlarge your knowledge, you are doing a favor to your colleagues also, which did not ask, but I mean they had the same doubts or the same misunderstanding. So this is only to encourage you to ask basic questions, and I'm not saying that I will succeed in answering all basic questions, because basic questions are the most difficult ones, but at least try. So, if on the meaning of what is written in the blackboard, if something, yes, yes. So, we are discussing about the quarks, and we also mentioned the gluons. These are the ingredients which are not actually necessary for the nuclear physics. Nuclear physics we don't know about, we don't talk about very often about quarks for part of nuclear physics, about quarks and gluons, but we talk about hadrons. So this is like I was saying at the beginning, it is there is a fundamental theory which is written in terms of quarks and gluons, and there is an effective description which is in terms of completely different objects, and these objects are the hadrons. Very different. Uh, Quarks uh, are not there actually. You cannot see a quarks, but it is a reality, let's say a reality, which underlies what you see in the experiments. And the experiments you see the hadrons. And the reason for this is very difficult to understand. The fact that these basic ingredients, the quarks, the gluons, are confined in bound states. And so you don't have access to their behavior. So, but their dynamics is very, very complicated. And as a result of this complicated dynamics, you have a phase transition, like in the superconductivity case, okay, just to give a physical image, okay. This phase transition is the hadronization, the change from a world of quarks and gluons to the worlds of hadrons. The world of quarks and gluons is the one which actually people study experimentally these world of quarks and gluons, and they do this in the high energy collision of heavy ions. So in this particular state of matters with very high densities or temperature, then then the easiest description is in terms of quarks and gluons. But when this plasma, this is called quark-gluon plasma, relax, okay, the temperature goes down, then these quarks, gluons, they hadronize, so they arrange themselves in bound state, and they form the, let's say, ordinary matter like nucleons or mesons that you measure in the detector, for instance. Okay. What I'm discussing is what is behind this hadron world. Okay. How this hadronic world, which is described in terms of nucleons, for instance, and particles exchanged among these nucleons, um, how this is related to this underlying quite hidden world of quarks and gluons. And one aspect which is relevant in the world of the quarks and gluons and in the worlds of hadrons is the chiral symmetry. Okay. Yes. Yeah. Okay. Sorry. Can you hear me? Yes. Okay. So it is chiral symmetry is a common feature of the rather abstract worlds of quarks and gluons and the concrete world of hadrons. Okay, a very concrete feature of the world of hadrons, because, for instance, as I was mentioning, the isospin symmetry, so the charge independence of the nuclear force, the fact that the nuclear force does not depend, is the same for neutron, between neutron and between proton and proton. If you interchange a neutron with a proton, nothing very crucial changes. And this is the same at the level of the quarks. If you change an up quarks with a down quarks, nothing crucial changes. Okay, as I was saying, this isospin is only a part of a larger symmetry which is twofold isospin, let's say. An isospin for the left quarks and an isospin for the right quarks. So the isospin, ordinary isospin, is the case in which, you transform in the same way the left and the right chiralities. I don't know if I have explained, but at least I have tried. Other questions? Yes, please. Yes, thank you. So, you're asking about the d// notation? Mm. Yes, yes, okay, thank you. So the quarks are Dirac fields, okay? So they depend on the space-time, x is time and space, okay? Also, I have not written, but they have a Dirac index. They are bispinor, okay? They have a Dirac index. This an index, let's say alpha, okay, actually is a bispinor, this psi, which which has 4 entries. Okay, on this vector, you have the action of the so-called gamma matrices. Okay, the Dirac matrices, which are 4 by 4 matrices. Okay, so when I write d/ in this notation, this is simply the contraction of space-time derivatives d mu with these gamma matrices, gamma mu. Okay, this shorthand notation for the contraction of d and gamma. Okay, so d/psi means that d mu gamma mu psi, where gamma mu is a 4 by 4 matrix acting on this indices. Okay, so if you like gamma mu, there are two indices, okay, spanning 4 cases. Okay, 0, 1, 2. Well, not 0, 1, these are spinor indices. Okay, so many indices that are too many, so one never write these indices, but every time there is a d/, there is a gamma matrix, so there is the presence of indices which are not written and are implied, so to say. So then there is a further aspect. Okay, let me say this capital D. Capital D is not the ordinary partial derivatives. This is the covariant derivatives. And I have written something like that, okay? Covariant derivatives. In the case of electrodynamics, this is the photon field, okay? A mu, the vector potential, okay? In the case of QCD, this is the gluon field, whence the notation G for gluons, okay? But there is a further implication which is not written, and if one is not used, one does not know, the fact that this quark field has a Dirac index, implied Dirac index alpha, but a further implied color index, okay? Let us call it I, okay? I is an extra index which goes from 1 to 3 different colors, or sometimes red, green, blue. The name colors has nothing to do, of course, it's just a further quantum number, okay, psi. And so all these objects are matrix also in color space, not only in Dirac space, also in color space. In particular, this one. This one is an object which has this structure. It is a matrix in color space, a 3 by 3 matrix. Okay, instead, the ordinary d mu is there is a Lorentz index mu, but then there is the identity for what concerns Dirac indices and the identity for what concerns color indices. Okay, these are implied. Dirac structure is in this gamma matrices. Color structure in these gluon fields. Okay, this is a new feature with respect to the QED with abelian T. Okay, so this is the fields of the gluons. Okay, there is not only one gluon. There is a matrix of gluons. Okay, a 3 by 3 matrix. Okay, must be Hermitian, and actually it is there are 8. Okay, this G mu, this matrix with color indices ij can be decomposed as the sum as the combination of these matrices lambda, which are the Gell-Mann matrices, are the generators of this SU3 symmetry. Okay, it's the generalization of the Pauli matrices, are similar to 3 by 3 Pauli matrices. Okay, why 3 by 3? Because here the symmetries for the gluons is SU3, not SU2 as we were discussing, but SU3. Color SU3, okay, because there are okay, color SU3. These are gamma matrices, and there are 8 independent gamma matrices. Okay, so this index, another index which is implied, is a further index which goes from 1 to 8. This is the reason why we say that there are 8 gluons. Okay, and so when we write something like this for quarks, okay, what we are doing is a kinetic term like that, psi bar e d slash psi. This d slash is what I have written here. There is the gluons here. So these are kinetic terms, no interactions, only two fields participating. Okay, plus a terms which is a coupling of quarks with the gluon. Okay, gamma mu is contracted not with derivatives but with this gluon field G. Okay, this is, you see, this is an interaction because you have three things participating. We express this situation with diagrammatically with a vertex which involves quark, antiquark, and gluon. Okay, but again, this is rather simplified because you could reestablish the color indices I in these quarks, color indices J in these antiquarks, and color indices in this matrix G mu I, is at least to clear the notation. Okay, don't know if it is more clear now. Yeah, the bar, yes, thank you. Yes, the bar, this notation psi bar for fermions, it is simply this combination. Okay, you have psi. this is the building block, then psi is a complex field. Okay, psi is not the same as psi dagger. Okay, it is somehow a charge field which is different. Psi and psi dagger are different, and it is convenient, instead of referring to psi dagger, to insert this psi bar. Okay, which is psi dagger gamma 0. Okay, so when we say psi dagger the slash psi, actually we are meaning this thing. Okay, gamma. So this gamma 0 is one of the 4 gamma matrices. Mu is a Lorentz index from 0 to 3. Okay. Also, a useful thing is that the gamma matrices satisfy the so-called Clifford algebra. Okay, so they satisfy anti-commutation relation like that. Okay, all these things um, enter in the description of the fermions of the spin 1/2 spin 1/2 particles. Okay, there are scalar particles which are invariant under Lorentz transformation, which are described by scalar fields. Spin 1/2 particles, which are not invariant, transform as a specific representation of the Lorentz group, and these are described in terms of these B-spin Dirac fields. They are called Dirac fields. Then you have vector particles which carries a Lorentz index mu, okay, like for instance the photons A mu, or the gluons G mu. Particles which have an index, Lorentz index mu, they are vector particles. There are other possibilities. There are spin 3/2 particles which carry Dirac and Lorentz indices, and the more complicated, the higher the spin, the more complicated the descriptions in terms of fields, which are irreducible representation of the Lorentz group. Okay, but don't need to discuss them. Spin 1 is enough. Other questions? Probably I will be able only to say less than what I had planned, but it's better to say less but understandable than to talk a lot about a lot of things in an ununderstandable way. Other questions? So let me discuss another thing, this psi bar. For instance, I talk about left and right-handed chirality also, no? Psi right is 1 plus gamma 5 psi, and psi left is 1 minus gamma 5 psi. You could wonder what is this gamma 5. Okay, gamma 5 is a combination of the 4 Dirac matrices. And gamma 5 has a special properties. It is a matrix which anti-commutes with all the Dirac matrices. So whenever you interchange a gamma 5 with any of the gamma mu, you pay a price. Okay. So this combination of gamma 5, 1 plus gamma 5 over 2, realizes what is called a projector. Okay, so 1 plus gamma 5 over 2 times 1 plus gamma 5 over 2 is equal to 1 plus gamma 5 over 2. It is a projection operator. P square equal P. Okay, projection operator. So this operation projects the spinor field on the right-handed chirality. Okay, they are different projection, different components of these fields, which is a 4-dimensional vector, B spinor, to be more precise. Right-handed projection on right-handed chirality, project on left-handed chirality. Of course, psi, if you sum psi right and psi left, you have recovered psi. Okay, no. The sum of the two gives psi. Okay. And also, if you project on the left chirality the right-handed quarks, you get 0, the orthogonal projector. Okay, why? Because 1 minus gamma 5, 1 plus gamma 5, this thing is 0. Okay, this thing is 0. And as a consequence of this algebra, you also have that a mass term psi bar psi. This is another ingredient of the Dirac theory. We have the kinetic term, which we discussed before, and also we have the mass term, okay, psi bar psi. And these mass terms actually can be written like that: psi left plus psi right. Okay, and actually can be written in this way with the different chiralities occurring. Why? Because you can easily prove that psi left bar psi left is equal to 0. Psi left bar psi left is equal to 0. Remember, what is psi left? Psi left is psi left dagger gamma 0. Psi left dagger gamma 0. Okay. What is psi left dagger? The dagger of this object. So we start from the right, psi dagger, and then we have to make the Hermitian of this 1 minus gamma 5. It turns out that gamma 5 is Hermitian, so the Hermitian is the same, 1 minus gamma 5 over 2. Then we have gamma 0, okay, gamma 0. Now we exchange this gamma 0 with gamma 5, we pay a price, okay, so it becomes psi dagger gamma 0, and then 1 plus gamma 5 over 2, okay, so this is psi dagger, okay, and this was psi bar left. It is psi bar times 1 plus gamma 5 over 2. When you multiply by psi left, which is 1 minus gamma 5 over 2, then you have this the same situation in which you have the product of the right-handed projector with the left-handed projector, and you have 0, okay? So this is why you have only the different, one says that master mixes the chiralities, okay? It's not the same with the kinetic term. Why? Because we have the gamma matrix. So remember, psi bar E d slash psi. This is the kinetic term, which contains also the interactions. As before, psi bar we can decompose in left and right-handed chirality. Okay. Then we remember that this slash notation means the contraction with the gamma matrices, and then psi left plus psi right. Okay. And in a similar way as we proved for the master, okay, you have that psi bar left gamma mu psi right is equal to 0. Okay. The difference with respect to before is that you have an extra gamma matrix. So in this movement of the gamma 5 matrices in the formula, you have an extra step, which, okay, makes that for the kinetic terms, due to the presence of these gamma matrices, okay, this mixing of the chiralities is absent. Okay, for this reason, the kinetic term is the sum of the diagonal, let's say, contributions. Okay, d slash psi right. Okay, so the kinetic term does not mix the chirality, and this is why we can rotate the left quarks and the right quarks independently. Okay. For the mass term, this was not possible. In the mass term, since you have terms like psi bar left, psi right, if you rotate the psi right, to get invariance, you have to rotate also the left, okay, chirality, in the same way. In the absence of the mass term, you are allowed to do that, okay? This is the reason for this symmetry, which is twofold isospin, twofold SU2, okay? And it is written like that. SU2 cross SU2, SU2 cross SU2. And one specifies for the left and for the right-handed chirality. Is that clear? Other questions? So, another thing that perhaps is not very familiar for someone is the fact that in the quantum field theory, the object of the interest is the time-ordered expectation value, vacuum expectation values of product of operators. Okay, in the quantum field theory, the fields become operators. Okay, to the students of one very often employs this hat notation to stress the fact that they are operators in an Hilbert space. Okay, so we take matrix elements of these operators, fields operators. Okay, matrix element, vacuum matrix elements of these fields operators, of products of fields operators, of time-ordered products of fields operators, time-ordered products. So the younger, I mean, it depends. This is the ordering depending on the temporal component of the space-time point to which the operators are attached, local operators. Okay, why? Why this is the object of interest? Why we should concentrate on these beasts, which are the green functions? Green functions. The connection is the reduction formula, the LSZ reduction formula. Okay, the fact that to inspect the properties of the particles, okay, we have to consider the matrix element of the scattering operator of the S matrix, and the S matrix, okay, are related to this object, to the green functions, okay, to the vacuum expectation value of time order product of local operators. Okay, these connections is the connections between the world of particles and the world of fields. It goes under the name of LSZ reduction formula. Okay, so a statement about the symmetry, current conservation, okay, is a statement about operators, because the current is an operators. Okay, so it is a statement about these objects, which are the green functions of the field theory. Okay, and so a convenient, although rather abstract way of express all these identities, which are called the word identities of the symmetry, okay, is to extend the symmetry, which is a global symmetry with parameters which do not depend on the space-time, to a local one, okay, to a local, as we did previously to derive the nether currents. Okay, so so imagine that these parameters of the transformation of the symmetry depend on the space-time. Then the Lagrangian, as before, Lagrangian is not invariant anymore. Okay, we have an extra term, delta L, which is psi bar left, VL dagger, and then there is I gamma mu d mu VL x psi. Okay, so if we subject left, if we subject the left chiralities to a rotation, an SU2 rotation, depending on the space-time. Okay, so from the kinetic term, we have an extra contribution when the derivatives act on the transformation matrix itself, so that we cannot use the fact that VL dagger VL is equal to identity. So we have this extra contribution. But we can remedy to this by adding to the theory a compensating term, okay, like it is done in the gauge theory. So we can act, if we add to the Lagrangian the coupling of this left-handed field to some external source, which is called L mu, left source, okay, and declare that this source L mu transform itself under the transformation in a specific way. Okay, so it transforms like VL L mu VL dagger, okay, plus no minus I d mu VL VL dagger. If it transforms in this way, so basically this term exactly absorbs the one written above. Okay, so we have, and we recover the invariance of the Lagrangian under a local chiral transformation. Okay, we extend a global symmetry to a local one, and the same can be done with the right-handed transformation by adding a corresponding source, which transform in this way, in a non-homogeneous way, in order to realize, to keep the invariance of the Lagrangian. Okay, so what we did in this way is to add to the Lagrangian these two terms, L mu psi left plus psi bar right gamma mu r mu psi right. This Lagrangian, these extra terms, is invariant under the local transformation, local chiral transformation, provided these external sources transform in this way. Okay, so L mu transforms in this way, and the same for R mu will R mu V R dagger D mu VR dagger. Okay, in this way. So these are the compensating transformation. Notice that this R mu, L mu, these extra sources are matrices. Okay, they are not numbered; they are matrices. So we cannot, for instance, commute this VR with R mu. Otherwise, this term would be trivial. Would be R mu equal R mu. Okay, so they are matrices, and these matrices, 2 by 2 matrices, can be decomposed in the algebra of the group through the generators of the SU2, analogously for for the right-handed sources. So we are adding 6 objects to the theory, which are called external sources. Okay, these external sources are 3 for the left-handed source and 3 for the right-handed source, and they couple to the nether currents. Okay, we have one external source for each nether current of the symmetry. Okay, so these amounts, this can be left as an exercise to this addition, gamma mu v mu plus gamma mu gamma 5 a mu psi. Okay, where v mu is simply the sum of the two external current and a mu is the difference. Okay, so what so you can prove as an exercise that these compensating terms can be put in this way, okay, as a sort of extra interaction, okay, of the quarks with external sources, which we can collect into in two by two matrices, L mu R mu, or equivalently in in two uh, 2 by 2 matrices V mu and A mu, okay, vector and axial. This couples to the currents psi bar gamma mu psi without any gamma 5 is called the vector current, and this couples to the gamma mu gamma 5, it is called the axial current. Okay, so we have equipped the Lagrangian with another interactions with this external source, which transform in this way. Okay, and also one can do something more. Okay, one can also equip the Lagrangian with coupling with other sources, not vector or axial vector, but scalar and pseudoscalar sources. Okay, so one can equip the Lagrangian with a term like that: S plus I gamma 5 P psi, a sort of mass term. Okay, a sort of mass term. These also S and P are the same external object, different external object in the same way as L and mu and R were. Okay, external object which are matrices. Okay, like the left and right external sources, and they also can be decomposed, for instance, but they don't carry the Lorentz index. Okay, they are scalar. This one pseudoscalar. Why? Because they couple to the scalar scalar density, scalar quark density, or P is coupled to the pseudoscalar quark density. Okay, pseudoscalar because there is the gamma 5. It is odd under parity. So also these scalar sources can be decomposed in the algebra. So these are 2 by 2 matrices. And also for the pseudoscalar sources, actually there are 3 independent objects, P1, P2, and P3. Okay, either we speak of 2 by 2 matrices, or we speak of 3 components of a general 2 by 2 matrices. Okay, so the Lagrangian is invariant under this local transformation, provided these sources also transform in the appropriate way. Okay, this source must transform in order to keep the Lagrangian invariant. They have to transform in the following way. Okay, this matrix S plus this combination S plus IP must go to the following thing: V right S plus IP, V left dagger, and S minus IP must go to V L S minus IP V R dagger. Okay. So please, as an exercise, prove that if we add to the Lagrangian the coupling to external sources L and R, or if you wish, V and A mu, V mu and A mu, and also you add scalar and pseudoscalar external source, then you do local chiral transformation. Okay, so you do transformation of with the space-time dependent SU2 matrix VL and the space-time dependent SU2 transformation VR, parameterized by 3 parameters space-time dependent alpha L and other 3 parameters space-time dependent alpha R. So the Lagrangian is invariant provided these external sources transform in this way L mu, R mu, as I have written, and scalar and pseudoscalar in this way. Okay, this is a second exercise to prove that under this transformation the Lagrangian remains invariant. Okay. So we started from this QCD Lagrangian, okay, involving quarks and gluons, added this coupling to external sources, and discovered that the symmetry is enlarged, provided the sources transform in that way. So not only invariant under global chiral transformation, but invariant under local chiral transformation. Notice that we have something similar to a mass term here, okay? This S must be viewed as a coupling with a mass term. And so we are considering situations beyond the case of massless quarks in practice. Okay, so we are extending considerably the theory. Now, these sources here play the role of a trick to make a symmetry local, but they are much more useful. Okay, they can be used to compute the green functions of the theory. Okay, so they can be used to define the so-called generating functional of the green function, which is best understood in terms of path integral. Okay, so the path integral is okay, the functional integral of this exponential of the action in the presence of these external sources. Okay, this is a different view of the quantum version of a theory. Quantum version of a theory can be obtained either promoting the variables, dynamical variables, the fields as operators, putting a hat, let's say. This is a way to obtain the quantum version of a classical theory. Another way to obtain the quantum version of a classical theory is to through the Feynman path integral. Okay, Feynman path integral. So this object is a measure of functional integration. We have to regard, let's say, the fields, the ingredient of the theory, okay, not as definite variables, but as fluctuating entities. And on these fluctuations, we do some average with this weight dictated by the action of the theory. Okay, so here what is fluctuating are all these fields of the theory. Okay, so we have one fluctuating entity for each point of the space-time. Okay, the whole fields is fluctuating. Okay, and we have to make an average, okay, of these fluctuations with this weight, the weight given by the action. Lost the notion of the time, so in 5 minutes. Now, if this is then a functional of the external sources. It is a number. This W is a number which depends on some function. So it is a functional. Which functionals? These external sources, V mu, A mu, S, and P. If I take functional derivatives of this object with respect to the corresponding sources, then what I'm computing, for instance, if I take minus I derivatives of this functional dv over the vector sources, okay, what I arrive at is this psi bar gamma mu tau over 2 psi okay. By deriving with respect to these external sources, I bring down from the exponent downstairs the object to which that source is coupled. In this way, the vector bilinear, quark bilinear, psi bar gamma mu tau A over 2 psi, because I derived with respect to the A component of this matrix. Okay, and so this is the average, okay, of these operators. It is a correlation function. Right. This correlation function is 0 by Lorentz symmetry. Okay, if I evaluate again in the absence of the sources, okay, equals 0, then I have this average, which is a Green function, a one-point Green function. If I take two derivatives with respect to two external sources, vector external forces, then I have something which resembles the object, the Green functions written above. Okay, in this case, the two-point vector Green function, time order product, okay, of two vector currents. Okay, so this functional contains a lot of things. By taking functional derivatives with respect to the external sources, you can compute and evaluating the result, putting the external sources to 0, okay, you can compute the Green functions of the theory, time order product, Bachmann expectation value of time order product of operators Which operators? The operators which are coupled to the external currents. In our case, the nether currents and also the scalar and pseudoscalar sources, which are very interesting for a lot of purposes. Okay, so the last equation that I want to write is the following. Imagine that you transform the sources. You have this generating function W. Okay, generating function of the connected green functions. Okay, I don't want to spend too much time in the details. Okay, it depends on the sources, external sources. Now I subject the sources to these transformations. Okay. Schematically, it is something like that. Now this is the same as a modified Lagrangian in the presence of the original sources, untransformed sources, provided this Lagrangian X is expressed in terms of the, let's say, anti-transformed fields. Okay, so provided the psi tilde, let's say, fields are related. Okay, for instance, the left-handed field are related to the in this way, anti-transform. Okay, so in this L tilde, what appears are not the original fields psi L, but the anti-transformed Y. In the same way for the right-handed chirality. Okay. Now, what are the fields here? Here we don't have any fields which are fluctuating. Fields are just dummy integration variables in this functional integration measure. Okay, so provided this measure is invariant under a transformation like that, then L tilde, this integral is actually equal to the original one, V mu, A mu, S and P. So we have that functional, generating functional is invariant under a local transformation of the external sources, that is of its arguments. Okay, it is not exactly true because for some of these transformations, the axial ones, the functional integral measure is not invariant. So we have the phenomenon of the anomaly, chiral anomaly. This was computed by Bardeen, Adler, and Jekiv. So there is an extra term here, okay, but which is explicitly known. In practice, the requirement of chiral symmetry is this equivalence, okay? The fact that the generating functional is invariant under this sort of chiral transformation of the sources, okay? And this contains all possible relations among green functions, quark bilinears, all the word identities, okay? So the effective theory is simply the expression of these functional integrals instead of as average on fluctuations of the quarks and gluons as average of fluctuations of something like order parameters, okay, of something else which is fluctuating, of some effective degrees of freedom. Let us call it U, okay, of a Lagrangian which depends on these sources and on these new fields, U, okay, in such a way to guarantee the invariance property. Okay, so this will ensure that all word identities are satisfied. So effective theory is nothing else that a representation of this generating functional in terms of other degrees of freedom, completely different than the original one, the QCD ones. But I apologize because I'm 2 minutes late and I stop here. Sorry to lost time for the questions. We recover tomorrow.